Okay, so today we're going to talk about more advanced PyTorch, like deeper topics than before, and some deep learning tools that personally I found extremely useful in my work. So it will be split in two parts. First, as I said, PyTorch and some topics that are more advanced. And then we'll talk about reproducibility, how to save models, and some external libraries that might help you in the project. So the first part will be useful for your homework 3. And the second will certainly help you in your final projects. Cool. So yeah, pay attention. Very important stuff. So let's start with the first topic, with convolution-like operations. So quick terminology recap for convolutions. There are different hyperparameters that you define in convolutional layer when you define it. So first is, of course, the kernel size, which is just the number of elements in each block. This is a 3x3 kernel, 5x3. You can play it whatever you like. There is also stride, which just defines the distance between adjacent blocks that you extract using the convolution. This is stride 1. This is with stride 2. Sorry, this is with stride 1. And next one is with stride 2. A less known parameter is dilation. And this is a distance between adjacent elements in the block. So this is a kernel with dilation 1. So the distance between each element is 1. And this is a kernel with dilation 2 in both height and width. So as you can see, we get a sparser window, but now it covers more ground. So that way we can get a larger receptive field, like more sparse, but larger, with the same number of parameters, which can be also useful. And the final thing is padding. It's just the number of elements that we add to the borders of an image when we perform convolution. And this is useful when we want to maintain spatial dimensions. For example, this is padding 0, this is padding 1. And as we covered the thing in my previous tutorial, when you have, let's say, a convolutional kernel of size 3x3, and you add padding 1x1, then you preserve the spatial dimensions, which can be useful. So in PyTorch, maybe you already know this, but it's very easy to define all these parameters. You just pass it as an argument to the NN module, like kernel size, stride, and padding. And the same parameters can be used in the max pool or average pool operations. So yes.
How do we specify the type of padding? Like, is it just zeros? Or?
By default, it's zeros, but there is like a border padding, reflection padding is like a string that you can specify. You can specify a specific constant you want to pad with ones or whatever. It's possible. But usually it's zeros. So let's say how you would actually implement the convolution-like operation. So first, there will be 3 steps for this. First, starting with an image of size h by w, you want to extract blocks. And we'll do this with function unfold. And I'll go into details what it does in the next slide. So it basically takes all the blocks in the image and unfolds them in one column. Then you apply some operation on the unfolded blocks, which are now columns. It could be a linear operation, it could be max pooling, whatever you like. And then with another function that is called fold in PyTorch, you fold them back to blocks. So in literature, if you would want to dig deeper into this topic, the unfold is called im to call operation, so image to columns, and the fold operation is called call to image.
The order is, in this case, would be like the row, the moving along the row.
Yeah, I'll go into unfold and fold in the next slide, basically. So yes, I hope it will be clear. So in unfold, you start, let's say, with a batch of images of size n by c by h by w. And then you extract blocks, as you said, in a sliding window. So the block size, so each column will be of size number of channels in the image. So in this case, it's c by kernel size in h, in height dimension, times kernel size in w dimension. So in this case, I had an image with 1 channel, and the kernel size is 2 by 2. So the column will be of size 1 by 2 by 2, so just like length of 4 for each column. And the other dimension of the output is just the number of blocks that fit into this image. So here it just goes over all the possible blocks in this image and extracts them in the column. Great. Is the intuition of unfold clear? Good. So in code, let's say you have a tensor of size 2 by 3 by 3 by 4, so 2 images, 3 channels, 3 by 4, and then you extract blocks with unfold with kernel size 2. So you get something of size batch by block size by number of blocks. So can someone tell me what will be the block size in this case? Yes.
Would it be 1 by 4? Or sorry, 2 by 4.
2 by 4.
You have 3 channels, so
3 channels, yes.
3 by 4.
3 by 4, yes, exactly. So like 3 channels, and it will be times 2 because the kernel size is 2, so it will be 12. And the number of blocks is 6. Right? Yes, it's 6 blocks.
What is the 4 in this case?
So it's like, not 4, it's like 3 times 2 because the kernel size is 2, so it's 2 in both height and width.
The original tensor, right? There's
What is 4?
2 by 3 and 3 channels, and what's the 4?
3 and 4 are spatial dimensions. 3 is height and 4 is width. It's just like the image kind of.
And the 2 and 3?
2 and 3 is the batch, the number of images. And
okay.
3 is channel of each image.
Yeah.
So you have like 2 very small RGB, let's say, images. So as I said, kernel size affects the output, like column length, the H dimension of the output, and the stride and padding affect the number of blocks. So if you add some padding, or if you make a bigger stride, it will change the output size.
So the unfold puts all of the channels in the same.
Yeah. If you have like, first it will take like all the kernel in the first channel, then in the second and in the third, it will be just like one underneath another. Great. The opposite operation of unfold is fold, and it receives blocks as input that you just extracted with unfold. And it also receives the output size, like the output size of an image that you want to create. Then it creates this image and initializes it with zeros. Then it iterates over the columns of the input and adds each element to its place in the output. So let me play this again, just for you to take it in. So in the code, it will be like this. We get as input blocks that we got from unfold, and we define the output size. Then we say torch, and then functional.fold with blocks, output size, and with specific kernel size. And then it just adds each element to a specific position.
So what happens in the overlap?
Yeah, good question. Actually, this is a question for you. Let's say we start with an H and W image, which was filled with all ones. We did unfold with kernel size of 2, and we one channel, let's say in this case. So we got the unfold result is just like columns of size 4, which are all filled with ones. So can someone tell me what will be the output at location 1 and 1? So you can see that like each block affects, like each element in the output can be affected by multiple blocks, and we add element-wise addition. So it should be 4 in this position. Is this clear? Great. So as you can see, the fold and unfold operations are not identical. So like they don't cancel each other.
If we need to make a Gaussian kernel, we can just use this.
I guess, but another thing that I wanted to say that might be useful when you'll you'll use this to implement the convolutional-like operation in homework 3. So if I remember correctly, at some point, you'll have to normalize the output of the fold such that it will be summed up to 1. And you'll have to think how to do this. And maybe this slide will actually help to come up with this solution. Great. Any questions about fold unfold?
What's the use of having it like this instead of being the inverse of I thought the whole point of unfold, like unfold is so that you can do all the operations that relate to a convolutional neural network, and then you want to put the thing back in, like back to the. So, but here we don't do the post, right?
Yes, it's not an.
So how is it useful?
So you'll certainly find it useful in like in your homework 3, but actually I haven't thought about like how to implement it such that it will be like directly invertible, directly like an inverse of unfold operation. We can discuss it in grade, okay? Great. So our next topic in advanced PyTorch part is how tensors are stored in the memory. So far you only dealt with tensor shapes that PyTorch reveals, and I think it could be a good idea to know, at least in high level, the underlying structure. So in PyTorch, the tensors are saved as 1D arrays in the memory. So, and depending on how exactly this 1D array looks in memory, we can call tensor either contiguous or not contiguous. So we call a tensor contiguous if it's saved in a single non-broken 1D array and it's saved in the correct order. So example, let's say we have a tensor of shape 2 by 4 with elements from 0 to 7. So in the memory, it will be saved as just like 1D array. And you can see that there are like no empty memory cells in between. So it's like non-broken single 1D array, which is one criterion for us to call this tensor contiguous. And the correct order is that, let's say for an element 0, to get to the next element in the same row, you have to skip 1 byte. And to get to the next row, you have to skip 4 bytes. This is the correct order. And if this is satisfied, we call this contiguous. This is like very useful sometimes in some operations because some algorithms work faster on contiguous tensors than are not contiguous tensors. And sometimes some algorithm will just like refuse to work if the tensor is not contiguous. And then PyTorch will shout at you and like say, please make this tensor contiguous. So you can check if your tensor is contiguous by just calling this is contiguous function. And it will turn. What can you do? You can just call dot contiguous, and it will just create a copy of this array by making a different entry in the memory. Yes.
Typically, we have like an abstraction between what we think memory looks like and what it actually looks like. So
yes,
why are we getting rid of it here?
Why we're getting rid of it? Like currently, like the goal of this part is to introduce to you this operation.
Oh.
So yeah, it's fine. So hope it will become clear in a few slides. So before, when you were trying to reshape tensor, you were doing it just with a reshape function, which is very useful and cool. But in some cases, for example, when you really care about how much memory you use, you might want to use this view function. So what it does, it doesn't create a copy of the tensor, but it just returns for the user the specified shape. So when you call a.view with the target shape, let's say the original was 2 by 4, and you call it with 4 by 2, it creates this view, and this tensor will still be contiguous because now you still need to get like 1 byte to the next memory, to the next element in the row. And now it's like 2 bytes for the next row in the same element, which is still contiguous and cool.
Does it change the chapter on the memory or?
No, the memory is still like, it doesn't touch the memory. It's
just changes the parameters.
Yes, like a tensor metadata, yes. Basically, it doesn't affect the underlying structure.
In reshape does create a new copy.
Sometimes, yes, we'll talk about it in the next slide. So sometimes it does, sometimes it just uses view. So there are some operations that actually break this contiguity. For example, transpose or permute operation. So let's say we applied transpose on the same tensor that we used as an example. And now you can see that to get to the next element in the row, you have to skip 4 bytes. And to get to the next row, you have to skip 1 byte. and this is not contiguous by definition. Right, so like if you just go into 1D array, like to get from 0 to 4, you skip 4 bytes, and then you need to get to 1, it's like -3, which is illegal, not cool, not contiguous. And
but still doesn't change. It doesn't create a copy. It's still the same.
Yes.
Again, you're just changing the parameters.
Right. Exactly. This doesn't change the memory layout of data. It's transpose and permit. And this view function is actually one of the functions that requires the tensors to be contiguous. And if it's not, it will throw an error. So for example, if you first apply transpose to a tensor and then tried to do a view, let's say like to flatten this tensor, you will get a runtime error because now like it cannot store a single like stride parameter how to access the memory. So like to get to the next element, you have to skip 4 bytes, then you have to do like -3 bytes, and this is an illegal view. So when you try to view a not contiguous tensor, it will throw an error. And as a reminder, this will never create a copy. This view will never create a copy of a tensor. But reshape can help you with this, but it will create a copy of a tensor. So when you're reshaping a not contiguous tensor to a view that the view function will consider illegal, it will just override the memory cells and create a copy of a tensor. Sometimes it's useful, but sometimes, for example, when you have huge tensors and you want to do reshape operation on them and you care about how much memory you're actually using, maybe it's a good idea to use view just to make sure that you're not creating more memory and you don't have any memory leak in your code. And reshape, you can use reshape always, and it will always work given that the shape is correct, like the number of elements match, but you don't know if it will create a copy or not. Yes?
What if I want to transpose and then rearrange? Let's say I know that from now on I'm only going to use the transpose matrix. Okay? So I want to transpose it and keep it like that and reset the memory.
Yes.
Array.
Yeah, so you can call this contiguous function, just this tensor dot contiguous, and this will create a copy in the memory. It will reset the memory. Any questions about this? Another? Okay. Great. Our next topic is how to load data in PyTorch. And there are two things in PyTorch that can help you with this. These are data sets and data loaders. So data sets are collections of data samples. It could be a collection of images and their labels. It can be a pair of images, or it can be whatever you want. It's very flexible. And data loaders are helpers that help you to load data from data sets into your model. And they're very good because they help you create batches, and they're supposed to be fast because they're using multiprocessing. Of course, you can write data loader yourself, but in this most simple way, you'll just use one process, and the PyTorch implementation of data loaders use multiprocessing, which will be much faster if you have multiple processes. So to implement your data set, you need to implement 3 methods: the init, length, and get item. And this data set usually returns a tensor or a collection of tensors in the shape of a tuple or a dictionary. So a simple example, you create your class of my dataset, which should inherit from the torch utils dataset class. In the init, you just define, let's say, a list of your images path and whatever transform you're going to apply to your images. Then you need to define the length of the dataset. So in this case, it's simply the number of images in the list. And the get item is the main function that will actually determine how the dataset will return the elements. So it will be called whenever you're doing this dataset of some specific index. And here you need to define the logic. So here you load the images, you apply some transform, and then you return, for example, a dictionary with key image and value, the tensor itself. Cool. And the data loaders, they receive a data set, the batch size, and some also other parameters as well, and they return an iterator. So here, an example how to create a data loader. You define a transform, you define your length, your list of images, and then pass it to the data loader. Just as simple. Then you just iterate it like for batch in data loader, and this returns a batch of images. So in this case, I defined a data loader with batch size 32. So the shape of the image that will be returned here will be 32 by the shape of images that you loaded in the dataset. And then you can do whatever with your images. Is this clear?
How large can this get? Like the list that you're passing with image paths can be like what, millions of images?
I guess, yes. It depends on how much memory you have. Like you need to store it somehow. So it's up to you.
You can just give a name of a folder and take every image in there.
Yeah, there are some like built-in dataset types in PyTorch that can work with folders of images. Yes.
So would I, for instance, would I arrange if I want to classify?
Mhm.
So would I arrange the folders names of and the names of the folder will be the labels, or should I have like
So
for training, a folder for
So for this, you should just go to the documentation of like it's called, I think, image folder dataset of PyTorch. I don't remember exactly how it should be arranged, but it is written there. Cool.
But there is a pattern that I should follow.
Yes, they will tell you what's the pattern. Next advanced topic is hooks, and hooks are useful when you want to access the intermediate results of your model. For example, when you're doing feature extraction of some intermediate layer, or you want to visualize the gradients like on GradCam, or you want to modify the intermediate outputs by regularizing some weights or by calculating specific loss that is applied only on some specific layer. And there are two types of hooks. Like hook is a function that is registered to either module or a tensor, and there are two types. First, it's called forward hooks. They can be attached only to modules. And for example, register forward hook. After you attach it to a module, this hook will be called, this function will be called after the forward call of this module. And there is also forward pre-hook, which can be called before the forward call of the module. There's also backward hooks, and they will be called every time a gradient with respect to the module output is computed, this register full backward hook. And you can modify the gradients that way of the for the module. And you can also attach the hook to a specific tensor and with this register hook function. And it will be called after a gradient with respect to this specific tensor is calculated. So this is a simple example of hooks. So here I wrote a function, my hook, which accepts a module and input and output of this specific model that I will attach it to, and it will just print something when it is called. To attach a hook, you just need to call this module. In this case, it's like model.conv1, where conv1 is just some convolutional layer. Then you call a register forward hook with the function that I just defined. And then whenever the model is being called like this net of x, just after the convolution, like this conv1 layer will be executed, there will be a print that we defined in the function.
So the hook is after what you...
There is, as I said before, here, there is like register forward hook and register forward pre-hook. So there are different hooks like for after and before, and also when you calculate like loss.backward, there are more hooks, but these are the main hooks that we use. If you want to know more, just go to PyTorch. There are a big list of hooks. This is very useful, maybe even for your projects. If you want to do some tricky stuff with intermediate layers, hooks can help you with this. Yes.
What is exactly the input and output?
So in this case, input and output are the input and output of this conv1 module. So this hook is called after, so it stores the input to this block and the outputs. That's it. And of course, you can remove a hook whenever you don't feel like using it anymore. For this, you first need to register it, and it returns actually a handle. So you need to store this handle. And then whenever you don't want to apply this hook anymore, you just call handle remove, and then nothing will happen. The network is called and the hook is not executed. Good? Good. So now a very short part. I think you should be familiar with this already, but the difference about training and inference. So the main important part in training and inference is set your model to the correct mode. There are two modes, this eval mode and train mode. And these modes affect different layers in your model. Mainly it's dropout, batch normalization, and it's also, I think, instance normalization, which I didn't put in this slide. So they just affect the behavior of dropout, batch norm, and instance norm. And you just, if you have those layers in your network, and you'll probably have them in your network, you need to always call the correct mode. So when you do a training loop, you need to call model.train. And when you do inference loop, you need to call model.eval. And just as a reminder, you also need to call with torch no grad just to spend less memory and to not calculate gradients. Cool. Yes. Our next topic. This will be last topic, and we'll go on a break after this. So our next topic is reproducibility. How to make sure. Yes.
Inference, you call them the actions that don't require training, like max coding and all these things.
No, by inference I say I mean when you want to evaluate your model.
Testing.
Prediction, yes. When you train your model and you want to evaluate how it performs, when you don't want to change its parameters, you need to call this model.eval and with torch no grad. Yes. So when you perform training several times, and if even you don't change any hyperparameters in your model, sometimes you might get different results. For example, you're tracking a loss, and one run it will go like this, the second run it will go like this, and the third one it will go crazy. And this happens because there is some inherent randomness in the process of training. And this randomness has several sources. It can come from train and validation split. It can come from some data loaders randomness. It can come from network weight initialization, or from some non-deterministic operations by PyTorch. So if you want your experiments to be deterministic, you need to do some work yourself to make sure it's deterministic. First, the main thing that you need to do is to fix the seed. So you need to call these functions. You need to fix the seed for Torch or Python. And if you're working with NumPy, you also need to fix the seed for NumPy. And after that point, like for example, if you will call these lines and then like create a random tensor, it will always be the same random tensor, which is very useful in some cases. But that's not all. That's not all that you have to do to make your runs truly deterministic. Another thing that you need to do is to tell Torch to use only deterministic algorithms, because some algorithms, some operations in PyTorch are using non-deterministic algorithms, and by setting this flag, you're getting rid of this. Also, there is some randomness comes from the cuDNN library, which is used to calculate convolutional operations in PyTorch. And it does actually a very nice thing. The first time the convolution is calculated, it's like running a small benchmark on different algorithms for your specific hardware, detecting which algorithm to use in the future for calculating convolution. And there is some benchmarking noise. So even for the same hardware, you might get different algorithms, which is not ideal. So this also introduces randomness. So by setting this benchmark to false, you make it select, you tell it don't benchmark and just select whatever you have, some deterministic way. And also you set the deterministic equals true, this good and deterministic equals true, to make sure that the algorithm that is selected for calculating the convolutions is deterministic itself. Clear? Amazing. Another randomness source can come from data loaders. So as I said before, data loaders are using several processes to gather data from dataset. So it's called workers, and you can define several workers that will query the dataset in parallel. And you also need to make them deterministic. First, you pass the generator with some fixed seed to the data loader itself. And then you also need to seed the workers such that they will all start with the same random seed. So there is an option to pass this worker initialization function where you just seed each specific process. So that way you'll get rid of randomness in the data loaders. Great. I think it's time for a small break, for 10 minutes break. Because next, we won't get a chance. Yes, let's continue. So our next topic is how to save and load models. Maybe you want to continue training, for example. And in PyTorch, there are two helper functions to save and retrieve objects from disk. Specifically, it's torch.save and torch.load. And torch.save receives an object. For example, it could be a tensor or a model, like some PyTorch class, and the path to where you want to save it. And then after you save it, you can load it with torch.load and a given path. So first way to save your model is you can serialize the entire object with weights and the class itself. So you can just call torch.save model and then give it the path where to save it, and then load it from disk whenever you want to continue training. The advantage is that it's very, very simple, right? You don't need to think about anything. But the disadvantage is that you can't change the model class. You can't change the code. So under the hood, this torch save, when it saves the PyTorch class, it uses Python's pickle model, which saves a path to the file containing a class, and which is used during the loading time. And if you change the some lines in that class and do torch load, it will break and it will not work. So this is not the best way to save models. Yes, you have a question?
So if I do it like this,
yes,
I don't need to define the model. It
saves
the model with its definition within.
Yes. So it actually saves the path to the file where this class defined, and then you do this torch load. It gives you back the entire object with the torch class and stuff like that. But if in the meantime, in between saving and loading, you changed some lines of code, even for example, you didn't change the layers in the model, you just refactored, just made your code prettier. This will not work. So a better way to save a model is to save its so-called state dict. State dict is the dictionary of weights and biases in your model. This state dict. So let's say for this convolutional model, the state dict will look like this. It is a dictionary where the keys are the names of the modules in the network. So it's like conv1.weight, conv1.bias, and so on. And the values in this dictionary are just the tensors themselves, the weights, the data that is stored in the weights of the model itself. So you can save only this state dict by calling torch save on the function model.stateDict. This model.stateDict returns you this dictionary. Then you can save this dictionary to a file, and then you can retrieve it from file with torch load. But in this case, you'll have to define, again, the model object. You'll need to define this model class with some parameters, and only then to update its stateDict with model.loadStateDict. Is this clear? This is how you're supposed to save the model weights. Save just the parameters. Cool. So another thing that you might want to save if you want to continue training is the optimizer state dict. There's also this thing for optimizers. For example, for Adam optimizer, during training, it calculates some running average for each parameter. So if you want to continue training after you saved your model, you also need to save this state dict of optimizer and then load it from disk whenever you want to continue training. If you want to do this for optimizer, then you might see this spike in your loss because it will start to calculate this running averages from scratch. For some optimizers, it's not critical. For example, for SGD, there are no parameters that it tracks, but for Adam, you need to do this. So in real life, we can do stuff like that. You can save a big dictionary where you save different state dicts like loss values and epochs. And then when you want to continue training, you just load this checkpoint in this specific, that's called extension, and you load the corresponding state dicts to the optimizer, to the model, and so on. All clear? Great. So our final part is the external tools and libraries that I particularly found very useful and that you might use in your project or in just your daily life when you do deep learning. So, and we'll start with how to use pre-trained models, where to get the pre-trained models that you want to use. So there are several ways, like several hubs for these models, specifically PyTorch Hub, from Hugging Face, from Torch Vision, or also from a package called Tim. And they're very, very easy to use. So for Torch, you can use this torch.hub load. You specify the name of the model, and you can also specify the specific weights for this model to use. There can be different instances of weights, maybe some trained it on this augmentation, some on different augmentations. Very easy, and you don't have to install anything. It just comes together with PyTorch. Another very easy option is just to load from Torch Vision Hub. It contains a little bit more than a Torch Hub, around 200 models. Or you can install another package called Tim, which contains, like, last time I checked, it was 2 days ago, 1,300 models, which is a lot. And then after you load these models, it gives you like a PyTorch class, which you can just inference on whatever data you want. Very useful, very easy. Yes?
Can we adjust the models, or are we just like given models and we like have to build something around it if we want to adjust them?
So you can adjust the models, like it gives you like a PyTorch module. So then you can replace some modules yourself. So it is possible.
Are they already trained, or should we train them?
You can specify that they're pre-trained or not pre-trained. You see this flag, pre-trained equals true. You can make it pre-trained equals false, or weights equals none, depending on the syntaxes there. And then they will be just randomly initialized.
Okay, thank you.
Cool. And another thing that I just want you to be aware of is this Hugging Face. This is an organization that manages like a hub for models, for data sets, and for demos. So like most recent projects, papers that, like, for example, in generative field, they all publish interesting demos on this Hugging Face website. Maybe it can be a good inspiration for your project. So maybe you can go to this website and just browse through demos to see what the other people are building. Maybe you'll adjust this and build something cool on your own. Great. So next topic is how to monitor your runs, how to actually track the performance of your models. And before that, I think in the homeworks, you're using a thing called live loss plot, which was plotting the loss curves and accuracy curves dynamically in the output cell of the Jupyter notebook. But when you're working on something larger scale, like your projects, for example, you'll need a better tool. And I suggest for you to use this weights and biases. And this is a amazing tool to track the performance. You can log like loss curves, accuracy curves, some media. And a nice thing is that you can work together. So this is like the logging is actually done on the website, and when you log in, like other people can also see the runs that you did. So, and it's also very easy to use. So you need to install it, of course, you import it. And then here in this block, I define some 5 dummy runs. So for each run, you first like initialize it, you tell the project name, the name of the run, and maybe some hyperparameters that you're using for this run. Then this weights and biases.init gives you a link, which you can follow and then track your performance. And when you actually want to log stuff there, you just call weights and biases.log. Here I logged accuracy and loss. And this gives you the, yeah, and you need to call weights and biases finish when you're done. And this gives you these nice interactive visualizations, which are very nice and accessible to other people in your team. And there are a lot of cool features in weights and biases. The features that I personally use all the time is just like filter by some specific hyperparameters. For example, you started the like hyperparameter sweep, and then you want to look only at the runs that contain this specific loss weight equals 0.1. Then you can filter it there. And you can also compare different run configurations. Maybe you forgot exactly what runs you are visualizing, and you can clearly compare that. Yes.
Is it locally or to some?
Yeah, so it's both locally. It's also saved locally in your PC in some specific folder, but it's also logged to their server. There are options to host weights and biases locally, but
Like TensorBoard, can you do it like TensorBoard with the local host?
yes, we can do this. But I think this is more convenient than TensorBoard when you're working with someone else. You don't have to start always the TensorBoard server locally. This is always there. You can check it from your phone and stuff like that. So you can log, for example, histograms if you want to check the gradients of your model to check that there is no vanishing or exploding gradients. You can log images, for example, by calling weights and biases.image. It's called on the tensor or on the build image. You can call you can log videos as well. And this is very flexible. I really recommend it for your final projects to use this. Any questions? Cool. Next, we go to some useful libraries for data augmentation and some transformation on your tensors or images. And the very popular, I think the most popular library for augmentations of your images is called Albumentations. And it contains a huge amount of different augmentations for different tasks. For example, for classification or representation learning. And it has a very, very simple syntaxes, which is very similar to PyTorch, Torch Vision syntax. You can compose different transformations. For example, here I compose random crop, then horizontal flip with some probability, and then the random brightness also with some probability. It is also very smart. It can help you apply the same augmentations to, let's say, bounding boxes. If you're doing detection, then if you apply the augmentation that crops an image, it will also apply the same augmentation to the bounding boxes that you provide, which can be very useful. It also supports key points. So it will also like transform the key points accordingly. For example, in this case, I cropped some key points, so it will remove from the list of key points. Very nice. And of course, it supports masks, which is useful when you're doing, for example, segmentation or some in-painting task. So yeah, use it. There are a lot of augmentations. Very nice library. Another library, which is also useful as well for augmentations, but not just augmentations, is Cornea, and contains a multitude of computer vision algorithms. And the twist is that the algorithms there are usually fully differentiable. So you can just backpropagate through them and like put them in the pipeline of your model. So maybe you want to train something tricky and you want to backpropagate through some algorithm. So maybe in Cornea it is already implemented and used. So some quick examples, what you can do with Cornea is you can, for example, find the perspective transformation to some plane. And this is, again, fully differentiable, very nice. You can apply different filters, such as blurring or edge detection. You can find like difference between sharpened image and not sharpened image. Again, all fully differentiable and very nice. And as I said, you can just stack some algorithms. In this case, this is just augmentations, but some algorithms are also supporting this syntaxes. You can just stack them in this nn.sequential that you imported from PyTorch, and it serves as like a layer in your model, which is also nice. Yes.
Are there a lot of papers that have augmentation during test time or training time? Sorry.
Are there a lot of papers that do augmentations during training?
Yeah, like
Yeah, everyone.
Sorry, let me rephrase. Not during not like you perform augmentations on your data set, and then that's like your new data set, and you train on that. Like you at some point in your model, you perform an augmentation.
I mean, like in the middle of the network.
That seems like what this would be useful for, right? Because if you're able to
So
to your network.
I'm not aware of just like in the middle of the network, like in between layers, but yeah, I'm not aware of such like inside the network. Like before the network, yes, all the time.
Then why does it matter if it's fully differentiable?
So it matters if you want to like you backprop maybe through your model, and now the input to the model was provided by some algorithm that you also want to backprop through. For example, like when you're working with geometry, you want this like geometry transform to be differentiable. This is also very useful. So that's where not inside the network specifically, but maybe like before and after the network, if you want to transform your output with something differential, that will be useful. Yes. Great. The next library is my favorite. Like I love this library, and I think not so many people are actually aware of this and use it. It's called einops, and this library makes tensor transforms such as reshape, permute, more readable, and it makes your code cleaner. And it supports NumPy, PyTorch, and other frameworks. So let's see what it can do. Let's say we start with some tensor of shape 2 by 32 by 32 by 3, which is like BHWC. And we want to move the channel dimension to the second place. So in plain PyTorch, which is just here in the comment, you'll call permute 0312. And of course it will work, but later, maybe you in the future, when you will read your code, you'll not be sure exactly what you did here. What did you move to which place? So in einops, it is much more verbose and readable. It accepts two arguments, the tensor that you're actually performing the transform on, and the string that defines the transform. And it's very similar to the einsum that we were talking before. And before the arrow is the source shape, and after the arrow is the target shape. So here I just moved the C, like every letter is assigned to each dimension. I moved it from the last position to the second position. Very cool. And it becomes even cooler when you try to apply to do some much more complicated operations. For example, here I wanted to unsqueeze, move the channel dimension to the second place, and then collapse the spatial dimension, the H and W, such that first go the columns and then the rows. So in PyTorch, you'll have to call permute, reshape, transpose. Later, you'll never guess what you did here. And in einops, it's very easy. You put 1 when you want to unsqueeze, you put C in the specific place, and to collapse the spatial dimensions, you just put them in brackets. And the order of letters in brackets actually matters. So here you see I put this WH and not HW. And this means that first it goes over the rows. So it goes like takes this column, then this column, and so on, and stacks them together. And if it was HW, it will take first row, second row, third row, and so on. This is...
When you put it in parentheses, what does it mean?
Huh?
What does it mean when you put it in parentheses?
So this means to collapse these two, like flatten this dimension. And you can do flatten in different ways. For example, if you have a matrix, you can go first over the rows. Like you can concatenate row-wise, right? Or you can concatenate column-wise. And the order of letters like actually defines, is it first row-wise or column-wise? So in this case, it's WH, so it's like first W and then H. This will be column-wise.
Can we use this in homework 3?
Yes. I'm like, I don't think that you can import stuff, but if you find a way.
Why do you have the 1?
1 is to unsqueeze. So you see at the end, I also want to unsqueeze the first dimension. This 1 tells you to unsqueeze. So it adds like an additional dimension there. So this is certainly useful for your projects, but in homework 3, I'm not sure it will be able to do this. And some operations are ambiguous. For example, here, I wanted to get back to the original shape, like to uncollapse, so like to make the spatial dimensions back. So here I need to specify the dimensions, like H and W specifically. So here it's like 32 by 32, because otherwise it will throw an error and we'll say like, I don't know what you want to do. Very useful stuff. It's not just rearrange. There are also some other operations which are maybe less useful than rearrange, but anyway. For example, reduce, you can perform some like calculate mean and max or minimum on some specific dimensions. And this is also very verbose. You just remove from the string after the letter, after the arrow, which dimensions do you want to calculate this operation on. You can also perform max pooling with this, like with some specific kernel, but you'll have to go to the implementation, to documentation to see it for yourself. I didn't put it here. And there's also a repeat operation, which is also useful. You just put the, for example, axis in the beginning, and then you can do repeat for 5 times. And again, this is full differentiable. This is very fast, almost as fast as plain PyTorch, but I use it all the time, and I basically don't see a difference in the runtime. Yes?
So, for instance, repeat that. Does it mean that, let's say you have an image, it will repeat the same image several times?
Yeah. That's what repeat is for. And you can repeat on different axes. So in this case, I repeat the same image. Maybe you want to repeat the same channel or the same row or the same column. And this is applied not only to PyTorch. It can also be applied to NumPy, and it will have the same syntaxes, which is also nice. Because in PyTorch and NumPy, there are different syntaxes between like transpose and permute. But with this, it's unified.
Keeps the contingency?
I didn't check, so I don't know. Probably not. In some operations, it shouldn't. Cool. Oops. And our last library, which is very, very useful for your projects maybe, is called PyTorch Lightning. And PyTorch Lightning is a research framework which is based on top of PyTorch, and it is designed to eliminate as much boilerplate code as possible. For example, you will not have to implement a training loop with this. You will be able to manage your device or like multiple GPUs much better, like much easier with PyTorch Lightning than with plain PyTorch. If you will be able to automatically checkpoint your model and many, many more things. Very useful. So this is a very simplistic example of how to train your model with PyTorch Lightning. The only thing that you need to define is like the Lightning module, like the init. In this case, I passed the model to the init, like my network that will actually perform something. For example, here I trained it this autoencoder on mnist digits. Then you need to define the training step, which is just the forward pass of your model and the loss calculation. And then you return the loss. That's it. And you need to configure optimizers. So here I configured the optimizers to optimize only the parameters of the model by doing the self.parameters. And then you're good to go. Then you define your data set. You call this autoencoder, this Lightning model, and then call trainer.fit. And in the background, it performs the training loop for you, this loss.backward call, optimizer step. If you have some learning rate scheduler, it will also do this in the correct place. So this simplifies your life a lot. So a small price to pay is flexibility. So even though it was designed as lightweight as possible and as configurable as possible, it is not as flexible as plain PyTorch. So in my experience, I found that not all projects that I worked with can be adjusted to the logic and to the structure of this Lightning module, but most projects can. So if you're just training something and you want to make your life easier, you can use PyTorch Lightning. Yes?
What about stopping condition for the training? How determine?
So here, I think by default, it will just train until you Control-C this, but you can set like number of epochs and stuff like that. Or were you talking about some early stopping?
Play with, let's say, giving validation data set that will determine the stopping condition.
You can pass, like this is a very simplistic example, just like this will work, this code will work, But of course, you can complicate it even further, like just adding the validation step, and then you'll have to pass the validation data loader and testing. So it is very flexible. You can do almost everything that you can do with plain PyTorch. Cool. Cool. So yeah, the main message from the last part is don't reinvent the wheel. There is probably a library that is already doing what you need to do in your project. So better to look for it in the internet, but maybe the libraries that I presented today will be helpful. And if not, yeah, then write it yourself. So thank you. If you have any questions, yes.
When you pass a model in these sorts of things like Lightning, the model means not just the weights and biases, means also like the structure of the model.
Yeah, you can pass to the init whatever. In this case, I just passed the network itself, like the PyTorch module, which is like some autoencoder, for example. But this you can pass to the init whatever you want, or you can define the model in the init. Maybe you don't have to pass it to the Lightning model. Yes, and the next week we'll have adversarial examples by Nivaim. He'll tell you how to fool a network with a little bit of noise. Cool. Thank you very much.
This is on Monday or?
On Monday.